Okay.
All right, can everyone see
Yes.
slides? Okay, I will mute myself then.
All right. Well, thank you, everyone. And thank you so much, Juliet, for putting this all together. So welcome to our very first colloquium of the spring semester. And today what we will be doing is faculty flash talks. We will do these today and also next week. So today will be pretty simple because there's only 5 of us. We did have a change. Michael Morgan will now be going next week. So there's only 5 of us. So we have plenty of time for questions, and there shouldn't be a major rush. So moderating for me should be pretty easy, but I will still, just in case, make sure that things are moving in time. Juliet, do you mind going ahead and setting up for the next, the first speaker? Great, so go ahead, Brad, I'll let you start off.
Okay, thank you. Well, it's great to be able to kick off this semester's colloquium. I'm Brad Pierce. I'm the director at the Space Science and Engineering Center in the building and also faculty within AOS. And what I'm going to talk about is using satellite measurements to try and quantify uncertainties in emissions, in particular nitrogen oxide emissions that are very important for production of ozone and air quality issues. I'm going to do these studies during a field campaign called LISTOS, which is the Long Island Sound Tropospheric Ozone Study that was in 2018. Next slide, please. So the question that we're looking at is, can we use satellite NO2 column retrievals to constrain NOx emissions? NOx is NO plus NO2. And this figure on the left is a slide set that was put together by Tommy Jasmine at SSEC. And it looks at, first of all, OMI, which is the sensor, the legacy sensor that measured NO2 column. And you can see it's fairly coarse in terms of looking at that total column NO2. And then we have TROPOMI, which is right there. And it's much higher resolution. And we're actually able to now resolve spatial variations that are associated with urban centers. The final image on the left-hand side is from the VIIRS day-night band. And here you can see very well the lights associated with the urban centers. On the right-hand side, this is New York City nitrogen oxide emissions from an emission inventory that was put together by the EPA. And you can see that with TROPOMI, we're actually able to get a structure that's fairly similar to the emissions that we are using in some of our air quality models. So next slide, please. So this is the basic procedure. I'm not going to go into details on this, but what we're doing is we're adjusting the emissions that are used in the National Weather Service CMAQ air quality forecast system. This is the operational air quality forecasting system for the nation. And basically we perturb that model, the emissions in that model, get a response to the column, and then use that information to adjust the emission inventories based on assimilation of the tropospheric NO2 column. And these are the results of the experiment. This shows reductions in those NOx emissions during the LISTOS campaign of around 20%. And you can see that they're closely tied to these different urban regions that I showed in the previous slide. Next slide. So the next question is, did our satellite constraint on NOx emissions lead to improvements or worse results? So here is the verification part of the study. We use measurements from an instrument, a NASA airborne instrument that flew during LISTOS. It's called the Geostationary Coastal and Air Pollution Events Airborne Simulator, or GCAS. It flew a raster pattern on a number of days, sometimes twice a day over Long Island Sound, and is able to measure at very high spatial resolution this tropospheric NO2 column. On the left-hand side are the measurements on August 16th. On the right-hand side is the CMAC control experiment without the emission adjustment. And you can see that the model's overestimating the NO2 on this particular flight date. Next slide. This is the results after we used tropomi to adjust the emission inventory. And you can see while it's still overestimating, there's a pretty significant reduction in the NO2 column. And so we can say that this has had a positive impact on the forecast. Next slide. Ultimately, what we care about is predicting ozone concentrations, since that is what impacts public health. So this is verification of the impact of those emission reductions on the ozone prediction from CMAC. On the left-hand side on the top, we have ozone LIDAR curtain from Tim Berkeroff at NASA Langley at Westport, Connecticut, which is right in the middle of where the highest ozone on this day was. In the bottom, we have the prediction from CMAC, the control experiment, and you can see there's very little enhancement of ozone. Ozone here is observed above 100 parts per billion. CMAC is predicting it somewhere around 60. Next slide. This is what we get in the tropomi data simulation experiment. And you can see by improving constraints on the NOx emissions using tropomi data, we've actually increased ozone production and we have better agreement with the observations. You will notice there's a shift in time in terms of when that enhancement occurs. And we attribute this to the resolution of the CMAC model not resolving the sea breeze that impacts Westport, Connecticut. Next slide. So the reason that we're doing these kind of studies with tropomi data is to prepare for the future atmospheric composition constellation. This will be 3 different satellites, 3 different instruments on 3 different satellites that'll be providing geostationary measurements of tropospheric pollution. Tempo over the US will be launched next year. Sentinel-4 will be launched in 2023, and GEMS actually launched last February, and we're just beginning to start looking at some of the data from GEMS. And this will give us a global scale, diurnally resolved observations of urban pollution, and that's what we have to look forward to in the future, and I'll stop there.
Great, thank you so much, Brad. We do have time for questions. If you have a question, you can type it into the chat, or you can also raise your hand. So if you don't know how to do that, at the bottom, there's a bar. You can click on the reactions button and there's a raise your hand feature. Just please unmute yourself if you have any questions. Any questions for Brad? Okay, then thank you very much, Brad. If anybody has questions later, we can have some time at the end to ask questions for any of the faculty flash talks.
Dan does have a question.
Oh, Dan, what is the spike in ozone in Zimbabwe?
The figure there is showing tropospheric NO2 column. And I believe that those are, so it's not ozone, it's NO2. And I believe those are emissions from smelting activities that go along there. So you're referring to this enhancement right here.
Any other questions? All right, thanks, Brad. Next up, we will have John Martin.
Thank you, Steph. There's almost no other variable that commands as much attention in understanding and diagnosing the behavior of mid-latitude cyclones as the vertical motion. Its characteristic distribution in the cyclone environment is what underlies the beauty of the storms themselves, as illustrated in this satellite image of a recent storm in the Gulf of Alaska. It's a real beauty. Unfortunately, vertical motion is almost impossible to measure. But as a consequence of its importance, a number of methods have been developed in the past decades to formulate reasonable estimates of its value. And a good deal of my research effort over the past dozen or more years has been focused on partitioning such calculations of the synoptic scale vertical motion into physically separate pieces with the goal of better understanding the interplay of the various dynamical processes that operate in the cyclone life cycle. So can we go to the next slide, please? Perhaps the most fundamental means of estimating the vertical motion comes from employing the isobaric continuity equation and integrating the divergence in the vertical, the so-called kinematic method. And with the advent of modern numerical weather prediction, that's brought with it dynamically consistent output data sets that really afford confident use of the kinematic method now in the current era. And here's an example of the 500 millibar kinematic omega from an intense cyclone that developed off the Carolina coast about 2 years ago. And the upward motion is shown in green, and it's nearly identical to the primitive equation vertical motion that's produced within the model integration, though I'm not able to show you that comparison. Next slide, please. We can play some interesting games with this kinematic method. For instance, here's the same 500 millibar level, but the vertical motion that results only from integrating the divergence everywhere in the column above 800 millibars. So I call it the upper tropospheric forced omega. It's a substantially smaller fraction of the total that we just saw. And then one more slide. The remainder is accounted for by considering only the divergence in the lowest 200 millibars or so of the atmosphere. So this partition is interesting in its own right, and we're currently exploring how it evolves through the life cycle of intense oceanic cyclones. So that's one method. Can we go to the next slide, please? An alternative method for estimating the synoptic scale vertical motion is the QG omega equation, and that arises from combining the thermodynamic energy equation and the vorticity equation at the level of the quasi-geostrophic theory. So here's an example of the 700 millibar omega that was associated with a really rapidly developing cyclone in the Gulf of Alaska in October of 2004. And green is ascending and yellow is descending. And this total omega can be partitioned into a number of separate components. The next slide, please. On the bottom left is the so-called transverse omega at the same time. And this arises from the part of the QG forcing that can change just the magnitude of the potential temperature gradient vector. So it's effectively showing you where to the extent that the QG system is able to do it, show you where the frontogenesis is and the resulting frontal circulations. On the right is the shearwise omega that arises from that part of the QG forcing that can only change the direction of the vector del theta. And you'll notice that these separate components have different geometries and different magnitudes. And as it turns out, these distributions are quite characteristic of this stage, the sort of mature stage in the cyclone life cycle. See this over and over again. And further partitions of the QG omega are possible and often insightful. In fact, one can separately identify portions of the total QG omega field associated with geostrophic shear and curvature vorticity advections. And doing so a few years ago revealed brand new insights into the nature of upper level frontogenesis. So it's not just for play. There's some really interesting things you can learn here. Can we go to the next slide, please? Unfortunately, a direct quantifiable relationship between the omega field, however you determine it, and the development and intensification of cyclones remains rather elusive. So in other words, there's really no analytic means by which to take these various pieces of omega and confidently isolate the portion of lower tropospheric development for which they are each responsible. Can we go to the next slide, please? I've tried inverting just the QG vorticity equation and keying on the stretching term, the last term on the right-hand side, and go to the next slide, where you could imagine that you could substitute any piece of omega into that d omega dp term and then invert for the height tendencies. But one finds that when one does that, only the thin layer near the level of interest has a direct effect on the inverted height tendency. For instance, if I was to look for 900 millibar height tendencies, dz/dt at 900 millibars, I'd really have to look at the column stretching from 850 to 950. And that seems, physically incomplete to me. So I'm not satisfied with that one. Can we go to the next slide? One could also appeal directly to the definitions of dp/dt in height coordinates or dz/dt in pressure coordinates. And there they are written out in all their glory. Next slide, please. But one finds that in both cases, reference has to be made to both omega and W. So there are some issues to be worked out there, both physical and mathematical. There are some older ideas I've been fiddling around with lately, like the Pedersen-Sutcliffe development equation or related approaches. But but given their lack of routine use in the current day, I suspect they're deficient in one way or another as well. And I'm kind of stumbling upon some of those deficiencies as we speak. So in conclusion, a seemingly simple and certainly fundamental question regarding the nature of vertical motions and their direct influence on lower tropospheric development, at least in my view, remains in need of new attention. So I'd be happy to hear any suggestions or any pointers to places I should look to try and solve some of this mystery. And that's it. Thank you.
All right, thank you, John. We have a question from Dan. How do you separate out the upper and lower tropospheric divergence contributions to vertical motion at 500 millibars? In a non-divergent fluid, wouldn't there be compensation?
Yeah, so what you can do, you use the so-called O'Brien method. It's developed by J.J. O'Brien in the early 1970s at Florida State, where you can do the vertical integral of the divergence, and you set, the top and the bottom to 0, and then you kind of make up, you do some compensation as you go up through the integration. And so what I've been doing is I've just been saying, I'm setting all of the actual divergence that does exist to 0 above 800 millibars, and then I integrate three-dimensionally and figure out what fraction of or what is the distribution of vertical motion that arises from just considering the surface to 800 millibar divergence. And then I do the opposite, where I zero everything out from the surface to 800 millibars and integrate everything that's remaining in the column. And when you add them together, you get the total, but they are separate pieces. So that's how I'm doing it, using the O'Brien method.
Thanks, John. Any other questions for John? I have a quick question, John.
Yeah.
You mentioned that two of the different methods of computing vertical motion, the kinematic method and using quasi-geostrophic theory.
Mm-hmm.
How do they compare if you were to compute omega using both of those methods for the same system?
That's a good question. I think there's a hierarchy in terms of replicating what you get directly from the primitive equation integration. The kinematic method at high resolution is pretty good. Gives you a really nice distribution of the vertical motions at most levels. It's not perfect, but it has a lot of the detail that the cartoony omega that you get from the quasi-geostrophic inversion gives you a really nice broad contour description of what the distribution of the vertical motions is, but it doesn't have quite the same level of detail because you're inverting a second order differential equation. So, but when you make a one-to-one comparison, you're usually not terribly disappointed that the QG looks pretty close to the full model omega, but the kinematic is better.
Thanks, John. We have a question from Jack. Did we ever use the kinematic method in 452?
No, we did not, because I was just kind of learning how to make it work in GEMPAC myself at the time we were in class, so we never did that. But Tanner is going to be working with me on some problems, Jack, that relate directly to this problem in the spring.
Any other questions for John? All right, great. Thank you so much, John. We will continue on to our next speaker. So next up, we will have Elizabeth Maroon.
Hi, it's great to, I guess, not really see all of you, but see all of you. So this is the 5-minute version of some work that I've been working on for the last 2 years. I'd like to acknowledge my collaborators at NCAR. So Steve Yeager, Gökhan Danabashoglu, Nan Rosenblum, as well as our collaborators in the European Union. This is paper 1 of a 2 or 3 paper set that's going to come out. So what we did was we were looking at a failed prediction. So this is very much trying to figure out what can we learn from failure. So a lot of my research is in coupled ocean atmosphere systems in the subpolar North Atlantic. So if you look here, I guess you can't see my mouse, the subpolar Atlantic is pointed out by that gray arrow. So it's kind of the mid-latitude section of the North Atlantic that's separate from the Arctic. Why do we care so much about this region? The reason why is that there's a lot of key ocean processes going on here. You've got the North Atlantic Current, which takes heat poleward. You've got deep water production in the Labrador Seas, as well as overflows to the east of Greenland and over the Greenland Iceland-Scotland Ridge. And because the ocean evolves more slowly and the atmosphere responds to any ocean heat content anomalies and sea surface temperature anomalies, it potentially gives you a slowly evolving source of predictability for the climate system on multi-year timescales. So when I say multi-year, I'm talking interannual to decadal, possibly even multi-decadal. And it turns out that our decadal prediction systems over the past decade have indeed shown skill. So that's the map I've got here on the right. This is an average of 5 to 9 years in the future for all of our possible predictions in one system going back from 1955 all the way through 2016. Red indicates where you have skill that can be attributed to your ocean's initial conditions in the model. You can see there's a big red area, and this shows you that most of the extra predictability that we're getting on 5 to 9 years timescales, prediction skills, sorry, is attributable to processes in the subpolar North Atlantic. So all of these slowly evolving ocean dynamics. So that's why we care about this. Oh, next slide, please. So what I've been working on is one of the few failures in the decadal prediction system at NCAR, the Community Earth System Models Decadal Prediction Large Ensemble. So on the left here, we have in orange, the Decadal Prediction Large Ensemble, subpolar North Atlantic sea surface temperature anomalies. The solid orange line is the ensemble mean. The spread about it is the possible range, min to max of all the possible ensemble members. You can see that the black line, which is observations in the same region, pretty well follows within the spread, except for this 1 year here in 2015, where the actual subpolar North Atlantic sea surface temperature fell well below the spread. Turns out, and this happened, so the map we have here, these are the predictions for year 1. And then if we go to predictions for year 3, you can see it's even further outside. And for year 5, it's even further. It's just a huge miss for the entire system. So what happened in 2015 in the subpolar North Atlantic? On the right, we have sea surface temperature anomaly in a map form for the summer of 2015. So this is JJA from the ERSST version 5 product. And you can see you've got this big, deep, cold anomaly in the subpolar North Atlantic from just to the east of Greenland, almost all the way to Europe. This was a near record event. A couple of the pixels in there are record, but not all of them. And it was an important event in terms of human dimensions as well. This event likely was a cause of the European heat waves in summer 2015. But in the terms of this one case study that I've done, this event caused a huge miss. And if we care about our prediction skills on longer than 1 year timescales, if you missed your first year's prediction, the error in that is going to propagate forward for your longer timescales. So 3 years out, 5 years out, 7 to 10. So that's what you can see on the left. So this isn't just a persistence of error. This is the errors are dynamically affecting the trajectory of the ocean and atmosphere system. Next slide. So I spent a good 2 years trying to figure out what went wrong. Can we predict it? And so we tested a dozen easily hypotheses. I'm going to go through some of the most fruitful. So first hypothesis, one possible issue. Maybe it's that our model, CSM, just is structurally deficient and it can't produce cold conditions as cold as that observed. So we went through and just used the entire CSM1 large ensemble, which is an uninitialized counterpart to the DPLE, and concluded that CSM can indeed predict cold conditions as cold as observed. So we rejected that hypothesis. Next hypothesis, we did a lot of investigation into this study in the atmospheric conditions that were necessary to give us this cold blob. In particular, North Atlantic oscillation was almost record positive during DJFM, December, January, February, March. Maybe CSM, which has some issues with blocking in the North Atlantic, can't produce NAO conditions as positive as that observed. Indeed, it can predict NAO, it can produce, not predict, NAO conditions as positive as those were the predicted, but it still was a rare event. So we reject this hypothesis as well. CSM doesn't seem to have any obvious glaring deficiencies. So now we start to go and check out the initial conditions. One of the big biases we found in the initial conditions was that the initial Barents Kara sea ice was way too low. There's a whole body of literature related to in the last 5 to 10 years looking at how does sea ice influence later atmospheric jet evolution. And so we took a look at, okay, if we improve the initial conditions so that we get rid of the sea ice bias, do we have a better atmospheric circulation in order to produce a cold blob? We did an experiment with CESM, and it turns out that this also did not fix our problem. So we rejected this hypothesis. Atmospheric variability is big, sea ice bias doesn't matter here. Next hypothesis was, okay, let's use some better atmospheric initial conditions. So we used atmospheric initial conditions from a reanalysis rather than what had been used originally. Normally for an ocean dominant problem on timescales beyond that of atmospheric weather prediction, we wouldn't expect necessarily the ocean initial conditions to make a big difference out, years beyond the predictability of the EMSO timescale, though this is obviously still an area of research. So we figured, okay, if atmospheric initial conditions are important on a seasonal timescale, maybe we need better prediction, better initial conditions. So we tested another experiment and it made the prediction worse. So we rejected that hypothesis. Next hypothesis was checking out the ocean initial conditions. We used a totally different method with a totally different set of initial conditions, hoping that this would improve the prediction. It did a little bit, kind of a mediocre improvement, but it's still, the cold blob was still much too weak. And these are just a couple of the hypotheses we tested. So we had a lot of negative results, but we learned a lot about how the DPLE works, a lot about its deficiencies, and things that it does well. And we also learned a lot about how the cold blob evolved and what was important for it. So I would like to use this as inspiration for students. Don't worry if you get negative results. You can still write a pretty cool paper. So this paper I got over break, I was putting back together the response to reviewers. I had very positive comments from viewers. This is actually the most positive of my career. So even if you have a ton of negative results, you can still put together a very nice paper thesis of the things that you learned from rejecting all of your hypotheses. So thanks for listening, and I'm happy to take any questions.
Thank you so much, Liz. That is very comforting. So we do have some questions in the chat. Brad asks, are the decadal trends during the 2000s in the observed subpolar SST anomaly significant? And is the model's inability to capture this for the year 5 predictions meaningful?
Can you go back to that second slide, Juliet? So let me take a look at that, make sure I'm remembering what that looked like. So year 5 predictions, one forward. So for the 2000s, that's coming off of the 1990s spin up of the AMOC. So at least that trend upwards has a physically motivated reason for why we think that at least transition was skillful. In the 2010s, can you read, let me check out what the rest of that question was. Are the decadal trends observed statistically significant? I would have to go back and double check if the ones from 2000s to 2010 are statistically significant. For sure, they fall within the range of the Ensemble, which is a good sign. One thing that we found in the last month is that the DPLE has difficulty predicting sudden 1 year-to-year shifts. And that's something we're still looking into.
We have a question from Henry. For the second hypothesis, did the CESM successfully predict the NAO conditions in winter 2015 and fail despite that, or was an inaccurate NAO prediction a contributing factor in the failure?
Good question. In the initialized predictions, it could not produce the NAO very positive conditions that were observed. And that's the reason why we didn't get the coal blob in there. So the two problems are linked. That is a very hot topic right now for the multi-year prediction community. There's one system, the one from the Met Office, I believe, Depressus. They have really, really good NAO predictability on seasonal to annual timescales, which clearly, at least in this case, CSM does not. So methods that, whatever they're doing over there, whatever extra special sauce they have, either in their model or in their initialization setup, probably would help in this case.
And question from Dan, how is the ocean spun up for a 5-year forecast?
Okay, so the ocean initialization is kind of complicated. So all the decadal prediction systems are doing things very differently, and CSM is one of the most different of them. Because we don't have ocean fields going all the way back to the 50s, I mean, we barely have ocean fields, to the 90s. That's an Argo thing that we have such great observations today. To get around this, what they've done at NCAR is they use an atmospheric reanalysis to drive an ocean-only model using the CSM ocean model POP. The idea being that the conditions that in this atmosphere-driven model will be closer to the attractor of the fully coupled CSM than would other more, that would conditions that are derived from a separate ocean reanalysis be. So you have atmosphere reanalysis, you drive an ocean model, and then you use that ocean model's state to initialize the model, initialize the fully coupled CSM1 DPLE. And then you just let it go for 5 years. There are still shocks, and there's improving this method and getting rid of the initialization shock from even this CSM POP driven model is still something that's being worked on. And this is a very different approach than what other folks are doing. Like a lot of other systems are using like ORS4 as ORS5 as their initial conditions. But using a reanalysis like that means that you're going to be farther off that your model's attractor potentially. This is something that needs a lot of work, and probably something that I'll be at least watching a little bit from the sidelines or helping with for the next couple of years.
One more question from Dan. So is your interpretation that the NAO is random and hence the event is unpredictable?
That is one interpretation, is that this event was not predictable. Not everything is predictable. And, that could be the conclusion from this paper, is this just wasn't possible. However, there is also a body of literature that is showing that fully coupled atmosphere-only models, as well as initialized prediction models like the one I discussed here, have too low of a predictable signal that they produce. And by predictable, so if in our signal we're talking about the part that's coming from internal variability that should be predictable, things related to the NAO in this case, or we also have external forcing. These two signals are starting to look like they're too low compared to just noise in relation to what you get from observations. So this is sometimes called the signal to noise paradox. And I'm helping out a little bit with a project at NCAR where they're investigating more of the issues with the signal to noise paradox. And if there is some structural model deficiency that's common to pretty much all of our GCMs that could be causing this. So the other interpretation is that this is still a model deficiency where we just aren't getting the predictable part of the NAO strong enough.
Steph, I had one question. It seems like it might be a follow-up. Could I ask it?
Yeah, go for it.
Thanks, Liz. Can you, for somebody who doesn't know much about this like me, tell me what the concept behind predictability attribution is?
Okay, wow, that's a whole course potentially. So in this case, what I'm thinking about with this signal to noise paradox issue, what they're doing is they are taking a look at low frequency signals in both observations and in ensembles, and they're comparing apples to apples. And they're saying, okay, if we can trace some low frequency signal to something slowly evolving like the ocean, we expect that the magnitude of these two signals should be about the same. And what they're finding is that the ensembles generally have way too weak. I can think of a paper right now in the Pacific where they find the same thing, that compared to observations, there's just something that's a little bit too weak about the predictable part in this signal. It's the quick 2-second version, but I'm happy to talk offline because this is something that confuses me a lot, is trying to figure out exactly what that means about the signal being too low relative to noise and how you best think about that.
Okay, thanks.
All right, thank you so much, Liz. We will have our next speaker, which is Greg Tripoli. Go for it, Greg.
Thanks. Well, I thought I'd talk a little bit about large eddy simulation of a hurricane. In other words, running resolution of about 250 meters. Next slide. So I thought I'd point out first what my research interests are. I like modeling. I do a lot of numerical modeling, particularly on the mesoscale or smaller scales, but tropical cyclones are what I've really focused on lately, cumulus and tornadoes and fine scales like that. And then cloud physics. I've done over the last 40 years a lot of work on cloud physics. I think I was the first actually to parameterize the ice physics in a three-dimensional model back in the 70s. So I've been working on all these things for a long time. But my recent focus has been on tropical cyclone export of potential energy into the environment via the outflow. And so my interest is a lot in tropical environment, how it gets to be the way it is, and the extratropical environment that is interacting with the tropical environment. And the mechanism that connects the two is the tropical plumes and the associated subtropical jet. So I have a lot of influence in these, or a lot of interest in these features. Next slide, please. So we did a numerical simulation of a storm that we observed during a field experiment, tropical cyclone intensity experiment of 2015, where we ran drops-on legs with rapid-fire drops-ons through tropical cyclone. And then I did some numerical modeling to try to explain what I see. And on the left-hand side here is kind of the numerical model domain, which you can see is a fairly large-scale domain that encompasses a lot of extratropics and tropics, working with essentially a 3-grid system. The outer box is grid 1, which has some interaction with an analysis system from the GFS analysis. And then the 2 inner boxes there are two-way nested meshes. And when I do a large eddy simulation, that's actually a 4th box in the middle of that orange box and down there, where I have 250 meters resolution in the eye wall of the tropical cyclone. For comparison of observations on the right figure there, you can see that the intensity of this storm was very large. It was, in fact, the most intense storm to this date that was ever observed in the East Pacific. The actual observations were down to about 881 millibars, with most of my resolutions of down to cloud resolving resolution. I was around 800 and something millibars, 888 millibars. And then when I went to large eddy simulation, I actually found a situation where I got down to the 870s. And it certainly could have existed in reality because we don't have that kind of fidelity in the observations, just sporadically measuring the surface pressure. So I think the actual simulation was good. The one thing we didn't get was the rapid intensification you could see there happening, but we eventually got the right intensity. Next slide, please. Now, as I said, I look at the outflow that's produced, and one of the interesting aspects of the outflow from observations, and I don't have that many slides here because I'm trying to conserve time, but the observations indicated that there was a very thin outflow jet actually 2 outflow jets moving away from the storm that were less than 1 kilometer thick, maybe just 500-600 meters thick. So very thin outflow layer. You might think of outflow as being much thicker, over several hundred millibars, but in fact, the outflow was very, very thin. And there was 2 outflow jets, one to the north and one to the south that you see over here. And these are 2 pictures. The one on the left is a simulation of the outflow looking at potential vorticity, and the pink values are near zero potential vorticity magnitude, with the gray value actually near zero. So that it's just the magnitude of potential vorticity, so it's the same sign on either side of the equator. But you can see the very low values of potential vorticity being exhausted from the center of the tropical cyclone to the polar direction and to the southern direction. On the right-hand side is actually tracers that are emitted, tracers that we flux into the storm at the surface, based proportional. The tracers enter the storm at the surface proportional to the surface flux. So you can think of these tracers, which are shaded there in orders of magnitude, but the orange shading would be the highest value. These massless tracers are proportional to the log of the number of air molecules that are actually coming out of the surface of the water into the storm. And so by looking at where those tracers are going to the north and to the south in the 2 outflow jets, you see that they go quite a distance. And what's shaded on there in the gray are the subtropical jet in the northern hemisphere and the southern hemisphere. And what we see are the outflow channel 1 goes to the south, and that feeds directly in to the northern side or the equatorward side of the subtropical jet in the southern hemisphere. And the northern branch, outflow channel 2, feeds into the subtropical jet in the northern hemisphere. So this is one thing we find, is that the outflow from these storms, which accounts for most of the energy that's actually added into the atmosphere. You know, the effect of the storm is to pump a lot of mass into the upper troposphere, lower stratosphere. And this mass contains low potential vorticity and high potential energy. And it has consequences. It goes somewhere. It's the outflow of the Hadley cell, in a sense. It's going to go somewhere and interact with everything else. And what we find in these tropical storms is these outflow mass plumes move into the northern hemisphere or even the southern hemisphere, and are directly consequential with the formation of these jet streams. You can see that jet stream is curved anticyclonically. It is the tropical cyclone. It's part of the tropical cyclone, the outflow portion of it in the northern hemisphere and even in the southern hemisphere. So the outflow jets are extremely interesting. And what's interesting about them is that they come up at a particular potential temperature. They're almost adiabatic. There's some loss of radiation, but it's relatively minor. And the outflow jets occur at potential temperatures, in this case, with this strong storm, about 372, 373 degrees Kelvin potential temperature, which is a very warm potential temperature up there. But by putting something up there, it goes into what Don Johnson used to call the overworld, that loses a connection with the underworld beneath, because it's such a high warm potential temperature that it has no way of being resolved in the tropics. And the reason it can't be resolved is because it's well above the level of zero net radiation in the tropics. So there's no diabatic loss of potential energy once it's put up that high, because the radiation is insufficient to do anything. So these tropical, so this potential energy that's put up there virtually has to enter the extratropics in either the northern hemisphere or the southern hemisphere to do anything. Next slide, please. This is just interesting. This is how the storm was initiated, and you can see the there's a gap up there in the isthmus of South America, Tehuantepec gap in the topography, and we have flow through that gap that produces that produces the vorticity that initiates this storm. It works very, very well. I mean, I initiate this from real data well before the storm develops, and it develops almost exactly in the correct place at the correct time because of this gap flow. So it's a very predictable event, the initiation, the genesis of this storm in the Pacific. And you could see the vortical centers in there. Basically, there's like large eddies, even in this resolution, which is only 1 kilometer here. But what I did is I simulated this at an even higher resolution. Next slide, please. And can you animate that? This is a cross-section through the storm at 250 meters resolution. And the vertical lines there are actually absolute angular momentum relative to the storm. And the color scale there is the equivalent potential temperature with respect to ice. And what you can see is the updraft or the upward motion, which I call the moist entropy current coming up the inside of the eye wall, is very narrow. And then it moves out in a very narrow airstream at the top of the outflow. One of the fascinating things about this outflow is it's almost entirely composed of equivalent potential temperature measured with respect to ice. Now, there is a theta E that's measured with respect to liquid water that's somewhat cooler by 5 or 10 degrees. And there is outflow at lower levels for a short distance. But that outflow at lower levels, it's hard to see it in here. You could see some curling around. That outflow tends to recycle back into the storm, such that the outflow associated with the ice particles in this very thin outflow layer in the inside of the eye wall, that outflow is almost entirely composed of air that experiences the latent heat of ice, which I found very fascinating. And that's one of the reasons why the outflow is so thin, because there's a natural sorting mechanism. The reason, and when I did trajectories of the air moving up in this vertical region, what I found is the trajectories come in and they're moistened by falling rain. So the rainfall outside of the eye wall, outside of the inner part of the eye wall, the rainfall raises the saturation point of the air just outside the eye wall so that it processes the air. So eventually only the air in the inside of the eye wall experiencing ice equivalent potential temperature is able to get out into the outflow, which is a very thin layer. This matches exactly what we're seeing in the data. We measured the equivalent potential temperature, or the potential temperature, the outflow in the data, the thickness of the levels, and everything of the simulations matches exactly. So go on to the next slide, please. So a few takeaways. It's interesting that these hurricane initiation is a very predictable event. We always wonder one of the reasons why they're so predictable. And when you combine the effects of local topography in the East Pacific with the movement of an easterly wave, then it turns out to be a fairly predictable event. Also, it's interesting that the same air molecules coming out of the surface of the ocean, which initially are water molecules, but we could think of it as air bubbling up, actually ends up in the southern hemisphere subtropical jet and the northern hemisphere subtropical jet. These jets are the outflow of that air in a direct way, not just wave movement, but the actual air. Also, in these simulations, the dropsondes agree very, very well with the simulation. And what's I think a new thing here is that the formation of this thin outflow layer is created by a recycling of air and the effect of precipitation. The ice or the liquid tends to move away from the inner eye wall because of the slant and drop into the air around it, which then moistens the saturation point and then recycles it back in, so that essentially the air moving up the inside of the eye wall is pure ice equivalent potential temperature, which is fascinating to me. So that's all I wanted to show, just kind of the sort of thing we do with the modeling.
Great. Thank you so much, Greg. We have a question from Angel. What causes the outflow to be asymmetric with respect to the TC and later to organize as large-scale streams?
the asymmetry seems a lot to do with the inertial stability of the surroundings, that the outflow tends to take the path of least resistance. And on the southern side of the subtropical jet to the north, or at least the increasing westerly winds to the north, you have a weakness, and that sends the outflow in that direction. The outflow is also sent to the southern hemisphere initially because the inertial stability is almost zero at the equator, right? So it tends to flow initially in that direction first, but then as the jet streams approached it, more of a westerly jet from around it to the north, then it went in that direction as well. So the initial outflow was to the south, where the normal primary band would go, but then it turned to the north, and this is typically associated with the way these storms recurve. Once the outflow jet connects into the westerlies of the northern hemisphere, that actually marks about the point when these storms typically recurve. But once it went in that direction, then the outflow jet produced a subtropical jet which was totally conformed with the outflow of the storm. So initially it connected into the subtropical jet that was there, but then it actually formed its own subtropical jet after that.
Okay, and one question here from Brad. If the outflow is at 307 Kelvin potential temperature, then it would seem that the tropical plumes would be entering the lower mid-latitude stratosphere. Is that the case, or does it stay in the upper troposphere?
No, it absolutely goes in the stratosphere. But the way it works is that the plumes are actually have some potential temperatures up to close to 390, a little bit, but mostly they're centered around 375. And what they do is, and I have more figures that I can show you this, they actually create a wall. The tracers and everything else push up against the extratropical atmosphere with these low potential temperatures, and then turn to the right along the subtropical jet. But what they do is they form a very steep fold in the tropopause, which we can call an overfold, where the air from the very warm potential temperatures coming in from the south actually overfold the tropopause into the northern hemisphere and tilt it so that they cause frontogenesis at lower levels. And there are situations where you can look and they actually will develop, and the effect of this is to develop a baroclinic zone underneath in the lower troposphere and bring cold air to the south in compensation. So they do go over at the levels of the mid-latitude stratosphere, but they tend to stay in the upper troposphere, lower stratosphere region of the tropics. And so it would be considered stratosphere in the exotropics, but it's still tropospheric air from the tropics, but the very top of it. Does that make sense?
Brad says yes. Great, thank you so much, Greg. So we will move on then to our last speaker, which is me. So in these last few minutes, I will present here. So for this flash talk, I thought I would talk about something that keeps coming up in my work. It keeps coming up in the various projects that I do. So for those of you who don't know what I do, a lot of my work deals with subseasonal to seasonal variability, and specifically the teleconnections associated with the Madden-Julian oscillation. But what we often see is this interference between the teleconnection patterns associated with the MJO and the El Nino Southern Oscillation during ENSO events. Before I talk about MJO and ENSO here, I wanted to kind of introduce what I mean by interference for those of you that maybe have not heard that term before. So for this, I just want you to look at this animation and ignore my titles on the left-hand side. So what you see here is what happens when you have a superposition of waves. So at the top here, you have these two thinner blue waves. They have the same amplitude. They have the same wavelength. And you can see that one is stationary, and whereas the other one is traveling along here. Now, whenever both of these waves in this cartoon example are happening at the same time, such that they are coexisting or traveling across the same medium at the same time, then the total net effect is what you see at the bottom, which is just the sum of the waves. So whenever these waves are both positive in the thin blue, then you get this large amplification of the net result here in the bottom. And whenever they are in the opposite sign, such that one is negative and one is positive, then they cancel each other out, right? So when they're of the same sign, this is referred to as constructive interference. And whenever they are of the opposite sign, we refer to that as destructive interference. So this is something that we often see associated with the teleconnection patterns of the MJO and ENSO. ENSO is persistent. It will modify the extratropical circulation in a persistent way throughout our entire winter season. Whereas the MJO is a tropical propagating system. So the influence over the extratropics changes throughout a winter season during MJO events. Next slide, please. Okay, so I'll talk a little bit about what MJO teleconnections look like during ENSO events, and then what I mean by this destructive and constructive interference. So at the top figure, what you see is 500 millibar geopotential height anomalies during La Nina events. So during La Nina, we get this, and I'm going to just focus on the Pacific for time, so we'll ignore the rest. But during La Nina, we get this geopotential height anticyclonic anomaly that you see there, where the dotting indicates that it's significantly different from zero. Now in the bottom, there's two panels, and these are the 500 millibar geopotential height anomalies associated with two different phases of the MJO. Now, because the MJO propagates eastward, we typically like to refer to MJO phases, where each MJO phase tells us where the MJO convective anomalies are during a particular point in time. So during MJO phase 3, which is the top panel, MJO convection is active over the East Indian Ocean. And this is what that teleconnection pattern looks like. Now, because we have this persistent anticyclonic anomaly associated with La Nina, this acts to retract the jet. And because of this, these much faster propagating, these higher frequency teleconnection patterns associated with the MJO are going to experience this retracted jet. And as a result, the teleconnection patterns associated with the MJO are shifted westward, right? So for example, in this middle panel, you can see that the anticyclonic anomaly associated with MJO phase 3 is to the west of the date line. And keep that in mind when I show you the El Nino ones in the next slide. Now, when MJO is in the opposite sign phase, so the convection is the opposite sign in the tropics, which occurs during MJO phase 7, then the teleconnection patterns look the opposite. And again, these are shifted due to the retraction of the jet. Next slide, please. Now during El Nino, here at the top, there is a cyclonic anomaly that persists through the winter season during an El Nino event. And now if we look at the MJO phases, so again, phase 3 and phase 7, during El Nino events, now, if you remember during La Nina, that anticyclonic anomaly was to the west of the date line. Well, now it's to the east of the date line. And that's because the cyclonic anomaly during El Nino, that's over the Pacific, acts to extend the jet. So as a result, MJO teleconnection patterns are shifted eastward. Now, this is a definite impact that ENSO has on MJO teleconnections, but something that's really important to keep in mind is to not just look at these figures in the bottom when you're thinking about subseasonal to seasonal predictability. You also have to think about how these teleconnection patterns are interfering, right? We have these wave patterns occurring at the same time. So for example, here we have a cyclonic anomaly over the Pacific associated with El Nino. And following MJO phase 3, we have an anticyclonic anomaly in the exact same place, right? These are the opposite sign. So what happens is there's a lot of cancellation between these two. And depending on what the magnitude is of these teleconnection patterns for a particular event, you may have no no predictability associated with ENSO or the MJO due to this cancellation. On the other hand, you can get constructive interference, such as that example here in the bottom. You get constructive interference in the cyclonic anomaly in the Central Pacific. And in this case, you can get an amplified response, and then the impacts may also be amplified. Next slide, please. And I'll go kind of quickly since I'm out of time here. So this is just one of the impacts that I've looked at in my work. So what you see here are anomalies of blocking frequency. So blocking is important because it's when you have a persistent quasi-stationary high pressure system. So when it's stationary, you're dealing with persistent changes in weather. So during El Nino, here we have 5, 10, and 15 days after MJO phase 3 at the top. This is where we have destructive interference. And you can see that there's no changes to blocking frequency relative to the mean, right? So we're essentially eliminating our predictability from the MJO and from ENSO associated with blocking. However, when we have constructive interference, now we see this significant increase in blocking frequency that persists, right, 5, 10 to 15 days afterwards, right? So this is going to be important if we're thinking about, for example, precipitation over North America. You can see something similar during for La Nina here in the bottom. I won't talk about those since we're out of time. Next slide, please. And the last thing that I'll mention, and I won't go into this too much, but this is a recent paper with Dan Weimont and Matt Newman, where we also found this interference to play a really important role. So what we did in this paper, this was looking at the optimal development of the Pacific North American pattern, or PNA pattern, which you see on the top right. That's upper level stream function in the color shading. And what we found, if you look in this bottom panel, these are time versus longitude diagrams, is that the optimal way to get a PNA pattern, so the maximum growth in the PNA pattern, is when we have an MJO and an ENSO occurring at the same time that go from destructive towards constructive interference as that MJO propagates eastward, and the sign of the teleconnection patterns forced by the MJO change sign to be of the same sign as the ENSO teleconnection patterns. So I will stop there. And we are out of time. I can take some quick questions if you have any. Otherwise, that's it. Thanks, everyone. Does anybody have any quick questions? I'll answer maybe one. I'm happy to talk afterwards as well if anybody has any other questions. Thank you, Angel, for liking my map projections.
I'll ask one, Steph. This was really interesting. It makes me feel like chasing the Pacific jet is a little bit going after the wrong animals because maybe it's really the jet is the manifestation of these constructive or destructive interferences. Could you comment on that?
I think that's, it's kind of almost a chicken and egg problem, I guess you could say, right? Because, you know, we're talking about different forced waves that occur in different time scales, right? Now, MJO does have an influence on the jet, but because ENSO is persistent, whenever the MJO reaches the extratropics is going to be dependent on what that subtropical jet looked like in the first place. So it's kind of tricky. I think that's a tricky timing issue because those teleconnection patterns associated with the MJO are going to have an influence on the jet as well. But I don't know. I think that would be, as far as, you know, which one to look at first is maybe a little bit tricky. I'm not sure what the best approach is for that. We'd probably have to test out a few different things.
I hope we can.
Yeah. All right, well, we are out of time. So thank you everyone so much for joining us. We had a great crowd and we will see you all next week. Thank you to all of our speakers. Next week, we'll continue our faculty flash talks. So hope to see all of you here. Otherwise, have a great day.